Welcome everyone to the week 7 tutorial session. Today I am Rati Ludhani, PMR FTA for this course, and I am pursuing PhD at Department of Mathematics, IIT Bombay. Today we will discuss some sample questions related to week 7 lectures. So let's begin. Okay. These lectures are related to the addition, multiplication, and various operations on species. So here this is the product one. So we need to find what is E dot E plus of 5. So all the E dot E plus structures on square bracket 5. So okay, let me recall what is E. E of U So E of U is just U for all subset U. Okay. So if we take any n or whatever we'll take, you'll just take. So there is just one structure on any subset that is the singleton U. Okay. So do you know what is E plus? So
It takes.
yeah. What is
I
E?
think E inverse is E plus, and E plus is E plus is assigning one more point to E.
Oh, okay. No. It's like a positive part. So basically, when it is empty, so it says E plus U will be the same U, which we have if U is non-empty, and if it is empty, then it will be just phi. So remember that these two things are different, because when you take phi here, then E of phi is what? Just singleton phi as a set inside the set. So this is still a structure. So there exists one structure on phi, but here there is no structure when U is equal to phi. So there is no E plus structure on phi. Is that clear?
Okay,
The
ma'am.
difference. Yeah, so it just says like you just take the positive part. Usually this happens with functions in analysis, if you have read. Okay, so yeah, this is E plus. Now what is the product? So if you want to calculate this, so okay, I should not write like this. So basically this bracket I should use this one, square bracket. So it's this is just fu, or maybe, so we simply write for this just fn. Okay, because the structure on any set is same as so f structures on any u of cardinality n is same as on you consider any different set, but if it has the same cardinality, then the structures will be same. Okay, number of structures will be same. You can define a bijection. So yeah, here we have to see, so we need to find out this value. Okay, the cardinality of this, which we usually do for generating function. So exponential generating function, we need to find out this value, and then we'll just take some end of this into x raised to power n by n factorial. So let's calculate what how to deal with this. So the main point is, what is E dot E plus? Let's calculate what is this. So E dot E plus of U is what? Can you tell me? Sorry, again this bracket I should use. So what is this? So the multiplication of two species is what? As a set. So first, not I mean like as a set as in how many, not how many, what are the structures on U, what are E dot E plus structures on U. So according to the formula, what does this say? You take U1 plus U2. Like, so basically, if you want to visualize
So
that, yeah.
E of U1 times E plus of U2.
Yeah, exactly. E plus of U2. Sorry, again there are square brackets. So you consider all the E structures on U1, and here you consider all the E plus structures on U2, and then you, as a ordered pair, you multiply, like it's just a ordered pair thing. And so it's like this is a set, this is a set. When you take the product, then the cardinality will be like m into n if it has m, and if it has n elements. Then, and you sum it up. Sum means, sum is again same as the sum operation. So E plus this, for example, is like E of U plus E plus. So basically you take the disjoint union, so that plus is coming into picture. Okay, so let's see what is happening here. So you have, for example, a different, so this is your U, then you take a partition and then apply E1 on it. Sorry, so here E and here E plus. So this is U1, these are U1 set, these 3 points are in U1 and the other points are in U2. So E and E plus, you apply so basically you need to find out the E structures on U1 and E plus structures on U2. Okay, so let's see what will happen when we do that. So this is, so firstly let's see when we will not get phi. So according to these two definitions, if you have if U is equal to phi, then there will be no E plus structure on it, and in EU you will get some structure for sure. Okay, for any you will get some structure, and there is only one structure, because EU is just singleton set U. So there is just one structure on U from this, and there is only one structure on U with E plus structure. So you have only one E plus structure on U. But if U is equal to 5, if that is empty set, then there is no structure. This is the difference. So let's see, if U is equal to 5, then we cannot, so this set will be just 5. This set will be nothing. So you cannot, so it's just empty set, EU1 cross empty set. So that is nothing. So you need to take all the sum such that U1 plus U2 is equal to U, and U2 is non-empty. Sorry, either I should write 0 or, so E2 is U2 is non-empty. Okay, so when you take this, now so this will give you something for sure. Now consider this. You have EU1 cross E plus U2. Then now what is EU1? So we are interested in the cardinality. So let's see what will be the cardinality. So cardinality is just because this is the disjoint union. So sum is the disjoint union. So disjoint union means so in disjoint union U1 U2, it's like this will be what? Cardinality of U1 plus cardinality of U2, if you want to find out the sum. Like in this set, what are the number of elements? Then you just take the sum.
Take the sum.
Yeah, because this is disjoint union. So if there is some element here which is same as in U2, then you will consider those elements to be distinct, and for that you can always do. So for every U1 you write elements U comma 1, for example. Basically you just consider this, and U2 cross 2. So when you take the union, these will be different, because there is the second position is 1 here, and second position here is 2. So these are going to be different. So when you take the union and take the cardinality, you will just get u1 plus u2. Okay, so in this summand, what will you get? You will just get summation u1 plus u2 is equal to u, and u2 is non-empty, and you take e u1, and there is cross, so you know that this is just ordered pairs, so the cardinality will be m cross n, so you just take this into e plus u2, right? Now what is this? You know that this is 1, this is 1, and we have removed the possibility of 0 because u2 is non-empty now. So this is just u1 plus u2 is equal to u, and u2 is non-empty, and u1 will be 1 and e plus u2 will be 1. So this is just sum of ones. Now what is the condition? Now for every u, now we are interested in, for example, we can just take n and we can calculate it. So let so here you'll get summation u1 plus u2 is equal to u, and u2 is non-empty, and this is just 1. Okay, so for example, now if we want to calculate n, okay, so this is u has cardinality n, then what will be the value? You are just trying to get the partition of u such that u2 is non-empty. Okay, so you are partitioning into two blocks, or the other way to see that, you can just think of like what you are doing, you have this, so for example here only you have this, you are trying to get one set. So if you get one set u1, if you get u1, then you the complement will be u2, so there is no choice for u2, so you just take all the subsets. So u1, you can think of this thing as or subsets of u. Okay, you can just think of all those v such that v is a subset of u. Now what we should remove, we don't want u2 to be empty, so that means you have to go just one down. So we have to restrict u is strictly contained in u, so v is strictly contained in u, so we cannot take v to be full u, because if we take u1, so or maybe
so for each of the elements we can take like 2 to the power n minus 1, because
exactly, yeah, you got it right. So you just take this sum will be exactly 2 raised to power n minus 1, because you are taking all the subsets but 1, so you're just removing 1. Note that if you take u1 to be empty, then u2 will be full cardinality n, and that is okay, because first operation, for first we are just applying e, and e of phi is still singleton set, so that is okay. So this will be just 2 raised to power n minus 1. So in our question, we have been asked to calculate this value for 5. So you will get 2 raised to power 5, 2 raised to power 5 minus 1, that is exactly 31. Okay, so yeah. Okay. So Mahalakshmi, I can just go through just once if you want me to explain it again.
Okay, ma'am.
So we were just doing the question was calculate e dot e plus of 5. So it's just the multiplication the multiplication of species, and it has been asked what it will be. So how many e dot e plus structures on 5 on the set
Set E5.
yeah, set this. Okay, so this is exactly the question. How many e dot e plus structures are there on the square bracket 5? So for that, what is e? Just to recall, e is just EU is singleton set U. So this is just the singleton set. Never think of the cardinality of U is considered here, because it's just one set. So there is only one E structure on every set U. Okay. So
Yes,
this
ma'am.
is this, and E plus U is singleton U if U is non-empty, and this is phi if U is equal to phi. So what is the difference? It says if U is equal to phi, the difference is only at only for empty set. So the E plus structures on empty set is empty, but if you take U to be phi here, E of phi, then you will get singleton set which contains phi. So this is still a set. So there is one structure on the empty set, but E plus says there is no structure on the empty set. So that is the difference.
Okay,
Okay.
ma'am.
So if you want to consider to get the cardinality, you have to recall that E dot E plus is what? This is just summation. You partition U into two sets, U1 and U2, and then you consider this summand. This sum. So sum E U1 cross E plus U2. This is the ordered pair thing. So you are doing the cross. Now here if you, so this is the value. Now you know that E plus phi, if you take U2 to be phi, then this is going to be empty set. Then in the cross product, like in this ordered pair thing, in this cross you will get nothing, because this is empty. So you can remove the possibility of U2 to be empty. So you can just remove U2, U2 is equal to phi. So I have just considered U2 is not equal to phi, and this is the thing. Now you take the sum. So this sum says again the same thing. Now you take the cardinality. If you want to consider the cardinality, you can just, this sum is disjoint sum, as in the sum of species. Okay, no, I should not write this. Like F plus G U is just the disjoint union FU disjoint union. So when, if you want to consider the cardinality, you can just add it up. So exactly this is the thing. So you can add it. So this is that sum. And now EU1, and when you take in the order, so these are sets, so cross of sets. So that is just if one set has m elements, another set has n elements, then this will have m cross n elements. Okay, so this multiplication I took with the cardinality thing. And now EU1 is 1, and E plus U2 is also 1, because these are singleton sets. Okay, so you get 1 into 1, and we have removed the possibility of U2 to be empty. So that means we are okay. So this is 1 into 1, and this is just 1. So these are what? These are exactly U1 plus U2 is equal to U. So you have this set. You need to partition that set in U1 and U2. So what you can think of, this set you can think of all the so if you get the value, if you get the set U1, then U2 will be just the complement of it. So there is no choice for U2. So you can just consider all the subsets of U. Then U2 will be, so that will be just U1. So U2 is just the complement of that. So there is no choice. So this set is actually U1 plus U2 is equal to U, and U2 is non-empty. So this basically is just the set, all the subsets such that V is contained in U. Okay, so all the subsets. Now we have to remove the possibility of U2 to be empty. So U2 cannot be phi. So that means U1, so when will it happen? When U1 is the full set, when U1 is U, then U2 will be phi. So you can say that U1 is, you can just remove the possibility of V to be U. So you just take strictly contained subsets. So that is just, you know that all the subsets are 2 raised to power n. So just you just remove one element, that is U. So minus 1, that is 31.
Okay.
Okay. So this is the question. move to the next question. The species E2 dot is isomorphic to which of these? Okay, let's see. What is E2 dot? Okay, so let's see what do we have. Yeah. Okay. So E2. So what is dot? Dot is the pointed species. That is what you take E2 and so do you remember what is E2 dot? So E2 dot
E2 dot of U equal to E2 of U cross U.
Exactly. So you just take, very good. So you take, sorry, not uh, as a set, uh, as the elements, okay?
Yeah.
Yeah. So you take this. This is E2 dot, and so yeah, the question is the species E2 dot is isomorphic to what? So these are like you have some uh, E2, so these are something like that, or you can write it in this way also. There are two ways to uh, denote that. So this is E2. So for pointed, you can just like you are pointing at this element. So this is the, okay, I don't know, the same thing. So you are pointing at this one element. So that is E2U. E2 dot. This is E2 dot U. Okay. So let's see. Okay. So, do you know any relation between, like, can you write something? There's one relation given in the class notes. So, we can also think of this in the form of, so, okay. Yeah. So, here,
X times
yeah,
X times E dashed.
exactly.
E2 dashed.
E2 dash. So it says you, if you want to get F dot, then you will do X dash. Okay, sorry, F dash. So how to see in the picture is so basically what you are doing, the pointed one, you just, so this is the dot we are doing. So you uh, this is dot, right? Yes, okay. So you have this, and you take E2, and you just take this pointed one, you remove it, and you take it to the different like you just separate it out, and at this place you take one extra element, okay, that is F dash. Okay, that represents F dash, and here you have this X corresponding to X, because X is what, X of U is the singletons. Sorry, when U is, the cardinality of U is 1, then you will get this. So this is this has a structure only when the cardinality of U is 1, otherwise you'll get just 5. Okay, so yeah, X dot F dash. So here what just to recall, so when you are taking U, you'll get X dot F dash U, right? Now there is a dot, so what you are doing, you are partitioning U. Okay, so when you are partitioning U, so X of so you know that you will get something only when u1 is 1, because the partition because when this is 1, then only it is non-empty and it has one element. So this is basically what, summation, or maybe I'll write summation when cardinality of u1 is 1, u1 plus u2 is equal to u. Okay, so you'll get x u1 dot f dash u2. Then what does that mean? u2 has n minus 1 elements. If you have n elements, then u2 has n minus 1 elements. Then f dash should be on the on. So f dash, what f dash does, it says you put extra point. So what is f dash of u? This is just fu, union, disjoint union again. You put extra element, or yeah, this is the notation. You take u plus. So what is u plus? U plus is u, and yeah, u disjoint union star. So there is one extra element, you add it to this. Okay, so that's why this is okay, because f dash u2 you'll apply on less number of elements. So this is basically f, I should write, and then this will become f, because this is on u2. So it need to have one extra element, that is dash, that will make the dash part. Okay, anyway, so yeah, this is the formula. So you have e2 dash, e2 dot is equal to x dot e2 dash. So yeah, this part is okay. Okay, but let's see if c or d could be true, because we don't know if uh, because that is all, that are also the possibilities, x dot e2 or even. So let's check it. Certainly e3 dash and e2 dash, when you see these are two different things, but not the others. Okay, let's see that. So x dot e2 dash, if you want to know what is this, then again you will do this. u1 plus u2 is equal to u, and you have x structures on u1 cross e2 dash structures on u2. Okay, so what will you have? So what is x? X is, you have okay, how shall I say? Okay, one more thing, we just better we don't try this. We can do that, but there is no requirement in this question. This question, the options are x dot e1 and x dot e2. So let's see if we can get something on e2 dash. What is e2 dash? If e2 dash is equal to something in e itself, then we can see if those options are correct or not. Okay, so what is e2 dash? E2 dash of u will be what? Okay, one more thing. Can you tell me what is E2, or in general what is EKU?
EK equal to set of U.
Yeah.
Set of U. Cardinality of U equal to K.
Yeah, set of U. That is like, that might confuse you. Don't say set of U. Just yeah, there is. This is the singleton set containing U.
Okay.
Yeah, I don't think u can be because this is singleton set. This is not this cardinality is not equal to the cardinality of u, because for example, if u is this, then this set is just 1 2 3. So this is just a singleton set. Okay, this is important, because when you take the cardinality, you have to remember this is just the singleton set. Okay, and the other set, if you remember, this elements one, this is actually u, and whenever, so this is actually just u. So this says there are there are u many structures, like the cardinality of u. So cardinality of this is actually cardinality of u. So when you want to calculate this, you'll get m. So this is the difference between these two e's.
Okay.
Yeah. Okay, let's see what do we have. So this is the singleton set containing u, and this will be phi otherwise. Exactly. So here e2u will be what? This is just cardinality. So singleton set containing u, if it has cardinality 2 and 0 otherwise. Sorry, phi otherwise. There is no other structure. Okay, so when you want to calculate e2 dash, so e2 dash is what? E2 dash u. So that is what does dash does? Dash like gives or I can write this extra element star. So you have some structure E2 and then you put a star into it. Okay, then so this is exactly E2U plus. So this has one extra element, so that means uh, so for example, because this is same on any u, so you can think of E2 or maybe okay. So now let's see, this is u plus, so this has cardinality. If u has cardinality 2, then this will have cardinality 3, right?
Yes, ma'am.
Okay, so so you are concerned, so whenever, so e2 dash u is equal to e2 u plus, so what can you say about this? When u plus is the cardinality of this is 2, then it will be this, otherwise this will be 5, right? So uh, you can simplify it and can write in terms of u. So this is u, this the sorry, this is the set, sorry. Okay, so star, okay, still doesn't matter because this is just one element. So this is now, you what can you say, this should be 1, right? Because u plus is 1 extra, so there is one element extra in that, so cardinality of u should be 1 to have u plus to be 2, the cardinality of u plus to be 2, right? And 5 otherwise again. So this is what can we say this is even or maybe isomorphic to even u, only u. So what you are doing, you are having singleton set when it is 1. I'm not saying this is the only thing we should check. We should check the bijection thing. When there is a sigma from u to v, then it should so you should get the bijection in terms of this isomorphism, right? So but you can easily see, because these are just the singleton ones, you can check. Okay, so this is what e2 u plus is isomorphic, or this is just e to u. So because of this, so for every u this is true. Is that okay? Or what I'm claiming, I'm saying this is same as e2 dash same as e1 is isomorphic to e1. Is that okay?
Yes, ma'am. Yeah.
So because of this, now we can conclude that e2 dot is isomorphic to x. Yeah, we had x here. X dot e1, right? So yeah, this option is also correct. Is that okay?
Yes, ma'am.
Okay. Okay, let's move to the next question then. Let f is equal to x of L. Yeah, now the composition is coming into picture. So f is equal to x of L and f tilde x has been asked. Okay, so let's try to compute again. So the formulas, if you know regarding this, I can just recall. So x of, for example, this is x1, x2 up to and so on is equal to z x L x1, x2 up to and so on, comma L x2, x4, and you'll have x L x3, x6, and you go on like this, right? This is the formula. Oh, sorry, this is z. Yeah, it does not make any sense if we write this L. Is that okay?
Yes, ma'am.
Yeah, so we try to get this, and we'll try to get f tilde of x, because again f tilde of x is you have to put x1 is equal to x and x2 equals to uh, so x1 is equal to x, x2 is equal to the power x square, and so on. You'll put this, right? So let's try to calculate this series. Okay, so yeah, f tilde x. So how shall we start? So we have a, so for this thing, what is required? So just first recall what is this composition. Composition says you take uh, you take u, so let's say this is your u, and you first partition it. Okay, so you partition it. So for example, this partition, and to each partition, so this is the set u, and to each partition you take the structure L, and on these structures, so these are like four, so four structure, so you have kind of rooted thing, so you have four blocks, and then over that you apply x. Okay, so so basically you are so in this situation x is applied to u, so applied to four blocks. So it's like you are applying to four. Okay, so you are considering, you are trying to calculate x structures on 4. Okay, in this situation, this is your composition. Now let's try to see how can we calculate this. So as you can see, for this, sorry, for this value, you need to find what is the cycle generating series for x and L, right? That is the requirement, because if you get it, you can just put the formula, use the formula, and get the value for this f, right? Is that clear?
Yes, ma'am.
Okay. Okay, let's try to calculate then. Do you know what is the cycle generating series for this? For x. So what is x? X is?
X
X is?
set u cardinality of u equal to 1.
Yeah, exactly. And otherwise, phi otherwise, there is no structure on other, if u is, the cardinality of u is not equal to 1, then there is no structure. And if cardinality is 1, then there is only one structure. Okay. So for this z x x1 x2. Okay, so we are calculating what is this. So this is from the sum. This is n greater than, or maybe we can write belongs to n. So we are including 0, no doubt. 1 by n factorial, and you will have again summation. You take sigma belongs to Sn, and f, now this is x, so I'll write capital X only. On n I can write, okay, and the cardinality matters, so it is not, will not create a problem. So you'll have this, and then x1 raised to power sigma 1. These are, sigma 1 is the number of cycles of length 1. Okay, and here you will get this, and up to and so on, xn, right? So you need to calculate this value. This is cycle generating function. So here firstly let's see, so it depends on if there is any structure on n or not. So here you know that this structure is there only when cardinality of u is 1, right? So cardinality of u is 1, that means n is 1. So n is 1, you just consider n equals to 1 then. So 1 by 1 factorial, you take sigma belongs to s1, and I'm just writing once again. So okay, so this is 1. Now sigma belongs to s1 means there is only one possibility. That means you just take sigma, because there is S1 is, there is just one element and you are permuting. So there is so you have one element, so you can so S1 is the set of permutations on 1, so you have only one option from this set to this set. So you just take sigma to be one element, sigma to be this cycle, uh, cycle or this permutation. Now with this sigma, how many this fixed points you have? So as x1 is again what, there is this singleton set, this is just singleton one, and so there is just one element. So okay, yeah, fixed point, so I should write in this form. So this is what, this is going from sorry, x sigma is the map from this to this, right? And this is what, this is your singleton set. X1 is this, and other side you are getting this. Now how many okay, in this situation there is one element, so it does not look too good, but there is just one permutation from the so sigma is just 1 goes to 1, so this is just 1 as a set. So these are we are taking a permutation, two permutations, so this is that thing. But okay, this, okay, in the next question or next to next question, you'll see how this behaves, okay, for bigger cardinality, because we can have S2 S3, okay, so you'll see there. Okay, right now you can see there is just one element to be fixed, because there is no other possibility. So it has to one is so this is mapping to one itself. So you have one fixed point, so you take one here. And what is sigma? The cycle length 1, and in sigma is just 1, because there is the cycle is just 1. Okay, so you have x1 raised to power 1 and nothing else, so we'll just get x1. Okay, is that clear? For 1 this does not look much, but yeah, is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so yeah, you have x1, so z of x, yeah, we are okay. Now let's calculate the other thing, this L. Okay, we don't need to calculate, we just use the result from the class. That is what, 1 by 1 minus x1, right, for the linear order. So you can see the proof if you want. So yeah, so you have so you'll get f x1 x2 up to and so on. Now what is the formula says? You take so you are calculating x of L, so x outside, and this is x1 x2 comma sorry, zl x2 x4 up to and so on, zl x3 x6 up to and so on, so on, right? So now okay, so what is zx? Zx says you just take the first so you just take the value for x1, so it's just x1. So you are actually doing this is composition formula. So is that clear? So I'm using zx thing. So zx says the value is x1. So x1 is what? X1 is this, the first coordinate. Okay, the first so first variable has this value. Okay, so you'll just take this, and this, you know, this is 1 by 1 minus x. Okay, is that clear? Is that clear?
ZX is also x1. Yes, okay,
Yeah.
clear.
Okay, yeah, and actually you can see that here itself. So you are taking x, okay, x on these things. So now what x does, x is, it has the unique option, like it has only one structure if the cardinality is 1 of the set, so here there we have partitioned in 4, so it is going to give 0 value. So if we don't partition, like partition as in one set itself, then so this is the partition, you are taking the full set in one block only, then only it will give so when you apply so L structure is there, when you apply X on it, then you will get only there will exist a structure. So you can actually see that so in there is this is the only case when you get this structure, and that will be all from L now. So it is just X of L is actually isomorphic to L. You can check that. Okay, so that's why you're getting even this. So it's just try to think visually, then we'll get the more intuition on this. Okay. Okay, let's move to the next question then. How many E of S2 structures are there on 6? Okay, let's try it out. Okay, E of S2 structures. So okay, same thing we need to do. We need to calculate this z functions and these things. So yeah. So this thing, so how many E of S2 structures are there on S2? So you need to actually calculate E of S2, or I can write 6 directly. So you need to calculate this value. So okay, tell me how shall we start?
Summation U1 plus U2 equal to 6.
This is not dot. This is of composition. That formula is for dot. Is that clear? Like we do this for dot only. You take all the other pairs and everything. So this is for dot cross.
So this is equal to E of S2 of E of S2 of the elements 6.
Yeah. Yeah, we need to calculate that.
E of S2 of 6.
Yeah, that we need to calculate, right?
Yeah.
So I'm just saying, how shall we start? Like, okay, so basically, what we know about these values. So,
So I mean, first S2 of 6 we need to calculate, then put like E of that thing.
yeah, we can definitely do that, and even we can. What was the formula? Yeah, E of S2 of X you can do, and you can so E of S2 of X, sorry, not this. So this is equal to this value. This is for exponential generating function, and when you get this value, you can definitely write it as the sum and do the what you want. So basically, you know that when you have f of x, this is equal to summation f u x raised to power n, where cardinality of u is n, right? So you can do that, or maybe better to write n greater than or equal to 0 f n. Sorry, there is n factorial also.
N factorial.
Right. So you can what you can do, you can get the what you can do, you can just you can first calculate the exponential generating function for S2, and also of ex, which we did earlier, I guess. No, it was for x. So for e we can do, and then we can do the composition, right? Then we can check from this value and get this coefficient, right? So this is one way. The other way, so basically we for e, okay, for e, do you remember? So I want to uh, also calculate what is the uh, sorry, cycle generating series is. Okay, let's try to calculate that also. Okay, that will be better to give you the intuition. So what is okay, first, so either way you can just try to calculate the exponential generating function, or you can start with cycle generating series also. Okay, so here in this situation, so what is e? Firstly, you know that as we did earlier, this is just u, and when cardinality, sorry, it does not matter what is the cardinality, it is always u, right, for every u. And what is it, s2? Do you know what is s2?
Yes, you means n factorial, ma'am. N2 factorial.
Yeah, that will be the cardinality. So yeah, you are going right. So can you tell me, like, it is the same thing as we split e as e1 e2, or l as l1 l2 l3. So what you will do, again, this is exactly su when cardinality of u is 2, and this is phi otherwise. So there is no structure on when u is not, the cardinality of u is not equal to 2, there is no structure. Otherwise the structure is su, and su is the set of permutations on u. Okay, so this is exactly, so you are saying, you consider all the set of permutations on u. So for example, if you want to write n, so you'll get the set of permutation. Now that is different sn form, the permutation group I can write. So actually you can write 1, sorry, 1 2 and 1 2. You just consider all the permutations. So when n is equal to 2, and this is phi otherwise. Is that okay? What is s2 now?
Yes, ma'am.
Okay, so let's try to calculate this, sorry, cycle generating series. So as I said, for s1 it does not look much, because s1, I mean this s1. Okay, I'm not saying as a species is this s1, and that s1 is different. Okay, this is in terms of species, and that is the permutation group. So let's try to calculate what is cycle generating series. I want to give you the intuition how we are calculating this series. So you have so you are trying to calculate zs2 x1 x2 up to and so on. So what does this say? Again, summation n greater than or equal to 0, or you can write n belongs to n, 1 by n factorial summation. What do we have? You take all the permutations. So you take sigma belongs to Sn, and you take now f is your s2 n. You take s2 sigma. You take all the fixed points, and then you take the cycles. Sorry, x1 raised to power sigma 1, x2 raised to power sigma 2, up to and so on, xn raised to power sigma n. So sigma is our number of cycles of length I. Number of cycles of length I in sigma. So you take the sigma belongs to Sn. You can always write it in the form of cycles, and so it's just the count, okay, number of cycles of length I in sigma. Okay, so let's try to see. Firstly, you know that S2n is non-zero only when n is equal to 2. Okay, so you can just consider n to be 2. So this summation can go with the use of n equals to 2. So you just take 1 by 2 factorial. Summation sigma belongs to S2, and you have S2 2 S2 sigma x1 is to power sigma 1, x2 is to power sigma 2, up to and so on, xn sigma n. Now, what are all the sigmas you can have in S2? In S2, now don't think of this right now. These, so this confusion can arise. So, sigma is here. Sigma is okay. Should I write it in different form? Or yeah, just sigma is what? Sigma gives gives two option. S2 is the set of two permutations, the identity one. I'm writing in the form identity, and the transposition. Is that okay? Transposition means the two cycles, so that these are the only option. This represents 1 2, this represents this 1 2. So 1 is mapping to 1 and 2 is mapping to 2 for this, and 1 is mapping to 2 and 2 is mapping to 1 for this, right? So there are two sigmas with us. So you take first sigma, for this first sigma is 1 2. Okay, so how many cycles are of length 1 with this 1 2 for identity? So I'm considering for identity here, I'll consider some. Yeah. So let's calculate this first. So x1 raised to power sigma 1, x2 raised to power sigma 2. For identity, how many sigma 1 are there? Like, what is the value for sigma 1?
2.
2, right? Because we need to calculate one cycles. So there are two 1 cycles. So you'll have x1 raised to power 2, right? And there is no sigma 2, sigma 3, everything is 0, because there are no 2 cycles, 3 cycles. We don't have that. We just have 1 cycles with this. So you will have x1 raised to power 2. Very good. Now you need to calculate this. So what is this?
X2.
Sorry?
S2, ma'am. X2. X2.
For this identity, so I am calculating this value right now. What is S2 to S2 sigma? Sigma is your identity now. Okay, so what are we doing? So this actually forms this structure. Okay, so let's see. So now what is S2? So you are saying S2 identity, this is the map you are considering right now. Okay, identity says what does this do? Okay, so here you have S22 is what? S22 is the set of permutations on 2. So there are two elements here, right? Where these are mapping, that is the point. You have 1 2 and 1 2. Okay, now what identity does? So this is what it is doing. It is identity is saying, so for example, for this element 1 2, okay, so what does this say? Identity is doing mapping 1 to 1 itself and 2 to 2. Okay, so this will map to this only. Okay, and this will map to this. So identity, it is doing nothing. What it is doing, but sending 1 to 1 and 2 to 2. Okay, so it is doing nothing. So this will be just so the fixed points will be 2. Okay, all the elements S, such that it is mapping to itself. So these are S. So you'll get 2 here. So here you'll get 1 by 2 factorial, and here you will get 2 x1 square. Now let's calculate the second one. Okay, so for second one, what is this? You have transposition 1 2. This is your sigma. So sigma is this. Now sigma is this. Then what will be this? Now sigma 1 is 0 because there is no one cycle now. You have just one 2 cycle. So you'll have x2 raised to power 1. Is that clear? There will be no other vector for this part. Okay. Now calculate this value S2 to S2 sigma. Okay, S2 to fixed points. Sigma is now 1 2 cycle. Okay, better to not confuse because I don't want you to confuse with these 1 2s. Okay, I'm writing like U1 U2 if you want. Okay, like this. There's just 2 cycle which maps first element to second element and second element to first element. This is what we have. So to calculate this value, what do you have? So the map says you have to take this, and this is your S2 U1 U2, this cycle. Okay, so what does this do? This is the set. This is the set. Okay, so basically if you have seen, this is if this how shall I say? Okay, so if the cycles, number of cycles, and like if sigma maps cycles to cycles, cycles of sigma to cycles of sigma, then we are done. Or maybe we can say if S maps cycles of sigma to cycles of sigma, then we are okay. So what it is doing? So 1 is mapping to 2 and 2 is mapping to 1. So so this stays as it is. How shall I say? Okay, I can yeah. So you consider so the calculation I'm trying to look at it. Okay, so for example, yeah, this is what S belongs to the fixed point. S will belong to the fixed point. So S is a permutation. It will belong to the fixed point if and only if S takes cycles of sigma, 2 cycles of sigma. Okay, so what does this say? So for example, in your situation, sigma is what? Sigma is U1 U2. Okay, now S takes, so S is what? S is 1 and 2. So 1 is mapping to 1, so it is okay. 2 is mapping to 1, sorry, 2 is mapping to, then it is okay. So it is mapping this element to this element itself. So what it is doing? It is doing, so it's like you will get, for example, if you have U1 U2, then it is mapping to S of U1 and S of U2. If it is still a cycle of 2 length, like if it is the same thing, like this, so basically you are trying to calculate, you are mapping this. If it fixes, then you are done. So S of U1 is what? S is your cycle 1. So here what do you have? So for example, if we just think of that, so S is your 1 2. So first element is this. Now you take and sigma is U1 U2. Now this is mapping to S of U1, S of U2. So if this stays the same, then we are done. So this will be a part of so, yeah, so S of U1 is what right now? S of U1 is okay. So S of U1 is actually S of U1 only, and this is S of U2 is just s of u2 only. And for example, if you take s to be equal to 1 2, then what does this do? u1 u2 sigma of u1, so if you take this, then it is mapping to s of u1, s of u2. Now s of u1 is what? It is s2, and this is this. But this is the same thing. That is the main thing it is happening. So it is what it is doing? It is mapping cycles to cycles only, the same cycle. Okay, the same cycle. So this s will be a part of su s sigma if and only if s takes cycles of sigma to cycles of sigma, which this is doing. So what is happening? So this value will be exactly 2. So just try to think of it, because like you are in permutation and you are using permutation, so that is the cluster you can get. Okay, so I hope this is clear, but okay. So I'm saying this will again be 2, so we'll get 1 by 2 factorial 2x1 square plus x2. Is that clear?
Yes, ma'am.
Okay. So this is 2 and this is 2 you are getting. So you'll get this, and from this you'll get x1 square x2. Okay. So you'll get, what has been asked? E of s2. Okay. So E of s2 of x1 x2, this formula says you will again do what? And e I'm not calculating. You know that E of x1 x2 is what? Is the exponential
x1 plus x2
sorry
plus exponential into x1 plus x2.
we'll get just okay, E of x1 x2 is what? We'll just get exponential of x1, right? No?
So, ma'am, x1 plus x2 lead to
You're saying exponential of x1. Oh,
plus
okay.
x2,
Oh, is that so? Okay.
x2 by 2.
Right. Sorry. Yeah. x1 plus x2 by, yeah, what was that? By 2 plus x3 by 3. Okay. Yeah, right. Yeah, sorry. So you'll have this exactly. Yeah. So you have this. So E of s2 will be what? Now you have to do this, and you need to find the composition, right? So now what you can do, so now you are concerned about calculating the E of s2 structures on 6, right? So let's calculate that. So what I'm doing, I'm just again doing x0 thing, and what will you get? E of s2, and what is the what will it do? So you can think of this to be s of s2 of x comma 0 and for the second part here it will be x2 comma x4, so you'll have just 0. So this will be, these are all will be 0. So this is the important one you will need to have, because when you put x1 x2 to be 0, then this will be 0. So you have this 0 comma 0. So what will you do? So E of x1 square plus or better you can just write x square, because this is just the exponential function, You can try to calculate this also, but it looks too big, so but yeah, you can do that. So e of x2, so now from the formula you know that what you will do, you have x square, so that will be x square plus x raised to power 4 by 2 x raised to power 6 by 3, right? And what is exponential? Exponential says you take x square plus x raised to power 4 by 2, 6 by 3 up to and so on. Yeah, so this by 1 factorial, that does not help. X square by x raised to power 4 by x raised to power 6 by 3 square by 2 factorial, and you go on, right? Yeah, now what you need to do, you need to find the coefficient of x raised to power 6, and also you need to go next step also, because x raised to power 6 right now, if you do square, then you will at least have, you can have x raised to power 6, but you you can go next step also, so this will be cube, right? Okay, I am changing the question. I've asked for 6, better to ask something less. You can actually calculate, that is not a thing. You need to find the coefficient, so, or you can try for 6. For now, let's say we want to have the value for 3. That is just calculation, so you have this. Okay, so I'm not going beyond that. You can try to calculate the coefficient, but that is something lengthy. So for x cube, what do you need? Okay, for x cube you will not have anything, so okay, maybe you can do 4 then. Did you get my concern? So when you do 3, you will get 0, so you can write 0. 0 is also an answer, but if you want to calculate for 4, then you can just go till this, and then for x4, coefficient of x4, you will get 1 by 2 here, and here you will get something that will be here 1 by 2 factorial into so how many will it be? So we are doing a square, so from this you will get 1 x raised to power 4, and with this multiplication you will get 1. So sorry, not multiplication, you will have only this x raised to power 4, so that will be just 1. Is that clear?
Yes, ma'am.
Okay, yeah, I'm just trying to calculate the thing, so you'll get 1 here, but when you are doing coefficient of x4 is this, but you are concerned about coefficient of x raised to power 4 by 4 factorial, so you need to multiply by 4 factorial. So why this is so? Because this we need for the from the exponential generating series, the coefficient of this is required as your so what was have we called f? E of s2, yeah, E of s2 of 4, so this will give this value, so you'll get 4 factorial. Yeah, is that clear?
Yes, ma'am.
Yeah, okay. So so basically you need to calculate from the formulas if required, but try to calculate this type generating series and better this cycle generating series, cycle index series, I guess. Yeah, okay, let's move to the next question then. Let f is equal to e2 or dot e2 dash, then what will be the value of fx? So e2 dot e2 dash, again so what you are doing, you are saying firstly you are, so for example you have u, so you are partitioning it, and then you are having, so so E2 and E2, so I should not say, yeah, partition is fine. So you are applying E2 on U1 and E2 on U2. So this is your E2 dot E2. Now you are adding one element. So for example this. So you are adding one element, that is your oh sorry, yeah, that's okay, yeah, that is your dash. Okay, so you are trying to calculate that, so let's do that. Then what is fx? So for fx, what do you do, what do you need to know? So fx is what, e2 of e2 dash x. So from the formula, what do you know? There's a formula related to it, it's like a differentiation. What is that? So it's just like f dash x is d over dx of fx. This is the formula we can use because, right? So you take d over dx of e2 dot e2x, right? Okay. So yeah, let's do that. So what is e2 again? E2 is the set, the singleton set U when cardinality of U is 2, and this will be empty set if yeah, this will be empty otherwise, right? So what will be e2 dot e2? So again for the exponential generating series, we need to have this value, right? If we can get this, then we can write the exponential generating function and we can complete the question, right? So what is e2 dot e2 u? Okay, again when you are concerned with the cardinality, again you can go by this, and you will have e2 u u1 cross e2 u2. Is that clear?
Yes, ma'am.
Yeah, okay, very good. So you are concerned for the cardinality, so you'll take sum over u1 plus u2 u, and you take e2 u1, and there's a cross, so or okay, it's fine. I went to this calculation first, but okay, tell me when will be what should be u1 u2, then only it will be non-empty. So
Either mod of u2 equal to 1 or 2.
1 is fine, is it?
Uh,
Sorry.
number of elements in u2 is either 1 or 2. Because u2 has to be non-empty.
Yeah.
u1 can be empty, right?
So e2 is this. E2 is this. E2 says whenever the cardinality of U is 2, you will get singleton set. Otherwise, it is empty. So there is only one structure when cardinality of U is 2. So there is only one E2 structure on square bracket 2, and there is no structure on uh, there is no E2 structure on any other set.
So if cardinality of u1 is 2, then cardinality of u2 will be. So what is the cardinality of u? Like n? It can be
Yeah,
n.
so
Okay.
we can track it down. So if cardinality of U, firstly what we are saying exactly as you said, if u1 is 2, if the cardinality of u1 is 2 and cardinality and, because even one of them is 0, then this product is going to be 0. So the situation when u1 and u2 both has two elements, then only you can get non-zero value in this summand, right? So you, in that case, and you are partitioning it, so u has to be 4, so the cardinality of u has to be 4. So whenever this is happening, so So what I can say, if cardinality of U is not equal to 4, then E2 dot E2 is going to be just 0, because you cannot partition, so whenever whatever partition you do, one of them is going to be 0. So in this sum you will get 0 plus 0, right? 0 plus 0 plus 0, whatever you will get. So if cardinality of U is 4, then you can have this value, you can have something. So, and what will be that something? U1 plus U2 is U. So you partition in 2. So when cardinality of U is 4, then you can still partition with 1 and 3. Like you take one element separately, 3 elements separately. So U1 has cardinality 1 and U2 has cardinality 3. Still you will get 0. So whenever the cardinality is 2, then you will get something, and that something will be what? 1, because there is only one element there is only one structure on 2, on square bracket 2. Is that clear? So these two things I can repeat if you want.
It's okay.
It's okay. Okay. So yeah, so with this, can you tell me how many elements will be there? So now again you just think of U1 as to be the subsets, because if U1 is fixed, then U2 has to be the complement of U1. So there is no choice for U1. So you just fix U1 and you can be done. So how many elements will be there here? So this sum, and so this is just you are summing over 1. So basically you are calculating how many U1 U2 could be there with these conditions. So again I'm saying, you just think of this and this. So you have 4 elements, you are choosing 2 elements, right? For U1 you are choosing, so you have for example 1 2 3 4. So now you are just choosing 2 elements. You can do it in 4C2 ways, right? Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So 4C2 will be there. So you will get 4 into 3, 2, you will get 6. Right? So there are 6 structures on 4. There are 6 E2 dot E2 structures on 4. So this E2 dot E2 x will be what? So you know there are structures only on only on square bracket 4. So this sum will be what? You just take, so okay, I can write E2 dot E2 of U x raised to power n by n factorial, n is greater than or equal to 0. So you will get only for n equals to 4. So you just write E2 dot E2, or maybe I can write 4 if you want, or you can write U with cardinality 4, x raised to power 4 by 4 factorial. So you'll get 6 into x raised to power 4 by 6 into x raised to power 4 by 4 factorial. So you'll get 1 by 4. So x raised to power 4 by 4. Okay, so this is your exponential generating function for E2 dot E2. But what was the question asking? You need to calculate this. So this is what? This is d over dx of E2 dot E2 x. And so you'll get, so what you are doing, you are just doing differentiation with respect to x of this. So you'll get 4x cube by 4, and you'll get x cube. Is that clear? So you have this option. Is that clear?
Yes, ma'am.
Okay. So, okay, let's move to the next question then. let R is equal to x plus e3, then which of the following which of the following visualize valid R enriched rooted tree structure? Okay, so yeah, let's recall what is R enriched rooted tree. So R enriched rooted tree. So what does this say? You have firstly you have R structure, R species of structure, species of R structure, that is better. So you have that, and what you are doing, you firstly for every so what does this say? For every U belongs to U, you consider yeah consider a rooted tree on so I don't remember how to write this, maybe yeah. So you consider all the rooted structures, so rooted tree structures on U, and and the second thing says, for every for every U belongs to U, consider the R structure, there exists a R structure on the children, okay, number of children. So yeah, the good definition, let's so you are considering, this is pointing, oh I missed, yeah, R endo functions, this is R enriched trees. So you take R to be the species of a structure, and R enriched rooted tree is on a set U consist of a rooted tree S belongs to AU. So you consider you consider S belongs to AU. So on every set U, yeah, I should not write U there, yeah, that is confusing. So you take any rooted tree on U, and second thing, for every U belongs to U, an R structure on the set of childrens of U, there exists an R structure on the set of childrens of U. So what does that mean? You have considered, so for example, this is your A B C D, these many points are there in U, okay. So you have U to be this A B C D and up to and so on, jitna bhi hai. Now what you will do, you consider the rooted tree. So you have considered this rooted tree, and now what you will do, you will take for every U belongs to U. So here for every U, so E C A K. So for example, on C, if you consider C belongs to U, there exists R structure on the set of children of U. So how many children are there? There is just one children, because there is one row going inwards to it. So there is one children. For example, for B there are three childrens, and for example for E there are three children. So there should be a structure on 3. So what this is saying, so there is E here, so there should be R of 3. So R of 3 should be non-empty. Okay, you cannot take the, for example, 0 set, and for example if you take the 0 species, then 0 species is like everything is 5, so there is no structure on any U. Okay, so if you consider that and you consider the rooted tree, then there is no structure, on this, for example on E there is no structure. Okay, so so you cannot have any R enriched tree there. Okay, so you should have some so R3 should be non-empty, R1 should be non-empty, there should be some structure. So you, for example, in E21 this cannot be or maybe better. So in this situation, for example, you consider E3. So if you take E3 of right now yeah, E3 of sorry, yeah, there should be something 0. So I am looking at so yeah, you consider E2. Yeah, you consider E2. Then what will happen? E2 of yeah, so E2 of 3 children, there are 3 children, okay? So the set 3, E2 of set 3 is 5, right? If the cardinality of U is 3, then it is 5. So if there are 3 children, so on the set of children of U, so on the set of children means there are 3 children, so the cardinality of U is 3. Then E2 of U is 5, because you know that E2 of U is only is the singleton set only if cardinality of U is 2. So in this situation there is no structure on E, you cannot have any R structure on E. So from this definition, there is no R enriched tree like this. Okay, so these are the requirements you should have for this. Is that clear? So the main thing is, so for example, with this so you have at the end you are saying, because there are no children, so you will get something at the end, because this is a rooted tree. So you'll for example, for this what is this, I can zoom. So this is for example D. So D has no children, so R of phi should be non-empty, because if it is empty, there is no array structure. Then the requirement will be like this second requirement will you cannot fulfill this requirement, right? So whenever you are considering any R enriched trees, then R of phi should be non-empty. Is that clear? So that is the one condition which have been imposed because of these first and second conditions. Is that clear? I can explain again if you need. Okay, let me know that. But let's move to the question then. You'll get more intuition there. So for example, you have this rooted tree. Yeah, this was something which was confusing. So you consider, so here for example, you have 1 3 4 5 2. So yeah, you are considering this. So now in this situation you have this rooted tree. Now in this rooted tree, and what is R? R is x plus e2 e3, right? So what will you have? X plus e3 is now you need to understand what is x plus e3. X plus e3 or better I'll write R of u, that is x plus e3u. What does this say? This will be what? Addition does what here?
Set U cross 1 comma
Oh, okay, in that sense.
U comma 2.
Okay, yeah, so basically what you are saying, you can take the union in this sense.
Yes, ma'am.
Yeah, this is one way, because we need to do the disjoint union. Okay, so for disjoint union you can write in this form. You just take the ordered pair with 1, and here ordered pairs with the second position to be equal to 2. Then in that case these are going to be disjoint. So xu so what we are doing, we are doing disjoint union. Okay.
E3.
Yeah,
E3.
E3. Yeah, exactly. E3. Thank you. So, what is XU? XU, you know, it is.
There are also 3. E3 U cross 2 or 3.
It does not matter. 1 and 2 are just the. Like it is just saying you can take anything. You take. For example, you can write A B if you want, and basically A should not be equal to B. So whatever you are writing, this is a way to write the disjoint product, sorry, disjoint union. So disjoint union says, for example, xu has something, let's say, I don't know, maybe u belongs there, and e3u also has u inside that, then u and u will be considered different. So we will consider the repeated. So with multiplicity we will consider it. So u and u will be considered different. So to write that, what we can do, this is a way to do that. So E3U cross B. So what will happen, even if you get, for example, here you got U, so then but when you take this element, then you will get this ordered pair, and here what we will get, U comma B, and you know that A and B are yeah, you raise the hand.
So ma'am, by mistake
Oh,
it
no
comes.
problem. Okay. So UA and UB you have. Now these are A and B are not equal. So that means these are not going to be the same. So that is a way to write the disjoint union, because you want to consider the same U to be different. Is that clear? So you can write A, B, 3, 4, whatever you can write anything, but that should be the different values.
Okay.
Yeah, and so here, for example, you can just consider u and u will be something different. These are not going to be the same ones. So this is said to be the disjoint union. That's why the sum will always be the cardinality of xu plus cardinality of x3u, because there is no intersection, because we are saying this is a disjoint union. So okay, yeah, xu. So what do you know about this? Xu is equal to u if cardinality of u is 1, right, and phi otherwise. Is that clear? Yeah, this is the way. This is xu, right? Yeah, I am confused. You can tell me. I think xu is this only.
Set U,
Yeah.
singleton set U.
Yeah, and this is, yeah, set u if cardinality of u is
3.
and phi otherwise. Yeah, these are the values for these are the x structures and e3 structures. Now what you need to see here, it says when you do x plus e3, so x plus e3, what will it do? You will either have any x structure on it, or you will have e3 structure on it. Okay, these are the two structures you can have. So what you are saying, when will it not have, will it not have these structures? So for example, if you know that if cardinality, so I can write it, yeah, so what I want to say, so if cardinality of u is 1, then you know that there is one structure on using x. So there is one x structure. And when the cardinality of u is 3, then there is one structure using, there is one e3 structure. But when it is not 1 or 3, then there is no structure, no x plus e3 structure, because if there is no structure or no x structure or e3 structure, then it is not going to be in the summand, because this is just the union of, either this will be it can have the, so basically the number of structures x plus e3 is going to have is just the sum of so for example, I can write x plus e3, the number of structures will be equal to xu plus e3u, right? So yeah, so when it will be non-empty, or I can just write, so this will be 1 if cardinality of u is either 1 or 3. So if it is 1, then it from x you will get singleton. There is one structure using x if the cardinality of u is 1, and if and that time e3 does not have any structure. And when cardinality of u is 3, then there is one structure from e3. So you will get 1 and Otherwise, you'll just get 0. Is that clear?
Yes, ma'am.
Okay,
Yes, ma'am.
great. So now, can you tell me what can go wrong in A? So, can there be a visualize valid R enriched rooted tree structure? So there is these are R structures. Okay. Now from the definition, what do you know? This R means there is a structure uh, on the number of children's on the set of on the set of children's of every element, right? So for example, in this situation with 3, so when you consider 3, the number of the set of children is just 1, that is this 2, right? So there is one children. In that situation, you know that there is R structure, because if cardinality of U is 1, because you are considering the set of children's, that will give you the cardinality. So right now in this situation, there is one R the cardinality of U is 1. So and in that situation, you know that there is at least one R structure on it. When cardinality of U is 1, there is at least one R structure. So this is okay. So so in the question says there should be an R structure on the number of on the set of children's. So you have to maintain that. Is that clear? For 3 it is okay. Now check for all the other things. So for example, for 1 you have 3 lines. So 3 lines means there are 3 children's. So in the set you will get 3, the cardinality of U will be 3. Now do you have any R structure on 3? On cardinality of U to be 3. So R3 basically. Is there any structure on it? So R is this. Right, there is one structure. So with 1 and 3 there are structures. So this is also fine. With 1 it is fine. So now check for 4. Can you tell me now? So how many children 4
4
has?
does not have children.
So
Children.
So 5.
yeah, so U cardinality of U is 5. Now with 5 you don't have any structure. So this is 0. 0 means now you are calculating the number of structure. There is no structure on 5 on empty set. So that is the problem. So you cannot have anything here. Similarly, not here, not here. So the requirement is not fulfilled here. So this is a wrong structure. This cannot be a R enriched rooted tree. Is that clear?
Yes, ma'am.
So now can you tell me about B and C?
B also
Yeah. Yeah, you were going.
similarly.
Yeah, the similarly 5 is the so as I said in the definition itself, 5 should have a structure, because these are rooted trees. You will not get any cycle. So these are rooted trees, so at the end you will get something which will not have any children. So on that you need to have an R structure. So 5 should have an R structure. But if that is not the case, then you are never going to get any any R enriched rooted tree there. So this is again false because of this, and again same here. So these will not be okay. So none of the above. Okay. So is that clear? So you have to think of that. So for example, if it is given for 5, then check for all the so what do we say? Yeah, I don't remember. So for all the elements you check that, okay, and you count the number of childrens and you consider that cardinality and check if there is any structure on it or not. Okay, this is a way to do that. Okay, let's move to the next question then. R is given to be 1 plus epsilon. So now you remember what is this? R of U is 1 plus this. And what is 1? 1 of E is 1 of
Empty.
uh,
U and cardinality of U equal to phi.
This is U. Okay, again I forgot.
Set U.
Acha,
Singleton
okay.
should be.
Okay, singleton.
No,
Oh,
ma'am,
okay,
no.
okay, okay. Yeah, yeah, yeah. Thank you. Yeah, singleton set U, and yeah, that sometimes confuse me also. So you have to consider singleton set. That is not just U. Yeah, and this is phi otherwise. And what is epsilon? This is you have this is just U, so there is no need to take the piecewise function. So you just take for all U, you'll just get U. Okay, so now let's see what we will get in this situation. So here this will be what, either it will have this structure or this structure. So now again you can try to get the cardinality, or you can think of in any other way. Just you have to count, or you have to check if there is uh, anything where it does not have R structure, and if that could be a count of number of children. So you need to check that. Okay, so here for example when you take 1, so now that is the case, this is U. So whatever, if you consider U to be 5, then only you will get 0, right? If you take 5, then it will be 5. So there will be no structure when U is the empty set with epsilon. But with 1 says there is a structure when it is empty. So 1 is fulfilling the requirement when sorry, not fulfilling the requirement, I'm saying it will give one structure at least, exactly one structure when U is equal to 5. Okay, I wrote cardinality. I should not write cardinality. If I'm writing cardinality, then I should write 0. So if U is equal to 5, then there is one structure with one U. So I can write in this way. So this will be 1 if cardinality of U is 0, right? Or U is equal to 5, then there is one structure with one U, right? And for other cardinality of U, like if U is not equal to 5, then you know that there is no structure from one U, but there are structures from epsilon. So from epsilon you have exactly U many structures, right? Because U is, for example, if U is 1 2 3, then there are 3 structures. So you always, as I said, singletons, this is a singleton set, but this is itself the set. U is the set. So you have to consider the number of elements which are there in U. So here you will get cardinality of U whenever U is not equal to 0. The cardinality of U is not equal to 0, or better, any case you can write U is equal to 5 and U is not equal to 5, or the other way, cardinality of U is 0 and cardinality of U is non-zero. Is that clear, this thing?
Yes, ma'am.
Okay, so now let's check. So yeah, the checking is actually okay, because now you don't have anything which is empty. So there is no U for which there are no structures on it, right? So 1 plus epsilon always have a structure on any U. Okay, so this is okay in that sense, because when you take 1, so there are 2 structures, and you know when cardinality of U is 2, then 2 structures are going to be there. When for 3, for example, there is one downside arrow, and so there is one children. So one children means there is one structure from this. And as I said, for empty set there should be structure. So for 2 5 and 6 there are no childrens. So for U equals to 5, you have at least one structure, so exactly one structure. So this is okay. And similarly, basically the point is there does not exist any U for which there are no structures on sorry, for which there are no structures exist for 1 plus epsilon structures exist. So for every u you have a structure. That is the main thing in this question. So in that case you can see A is okay, B is okay, because there is nothing which can go wrong, right? And C is okay. So all of the above. Is that clear?
Ma'am, that solving part now I can understand, but using the solving part, how to this diagram is correct or not, that is
Okay.
not clear, ma'am.
Yeah. So diagram, so what does this say in the diagram? So diagram means it says these two conditions should be fulfilled, right? So for any R enriched rooted tree structure on a set U should consist of these two things. Okay, this definition says these two things should be there. So we need to see if these conditions are fulfilled in the diagram or not. So this diagram is actually explaining sorry, this thing, right? These two things. Now what does this say? A rooted tree S belongs to AU. So you have a rooted tree. So you can always have rooted trees on U. So you have a set U, for example, any set in for example, in this situation, 1 2 3 4 5 6. This is your U in this case.
Okay,
Okay.
ma'am.
uh, in this situation, but I don't want to write it, because when you consider the number of childrens, then you might confuse with this U. So I don't want to write that. So what do you have? These two conditions says, so first condition should be fulfilled, that is okay, you are considering a rooted tree. Okay, so a rooted tree S belongs to AU. Now so this consists of a rooted tree S belongs to AU, which is there for everything. You have a rooted tree, so these are rooted trees. Now, and root, one is the root here, here one is the root, here again one is the root. You can have different, maybe you can have two as root. For example, in this situation you had 1 3 1. You can have anything as your root. That is not a problem. So you consider a rooted tree. Now for every U belongs to U. So rooted tree is on U. So these are the elements 1, 3, 4, 2, 5, 6. These are U belongs to U. So these are these. An R structure. There should be an R structure on the set of childrens of U. So what does that mean? Childrens means, so for example, if you consider 3 belongs to U, this one, if you consider this, then there should be an R structure on the number of, on the set of childrens of U. And what is the set of children? So you have 2. For example, for this 4, if you consider 4 belongs to U, this one, uh, all belongs to U basically. So I'm just considering this element. If you consider 4, then the set of children is 5 and 6. So it says there should be an R structure on this. So R structure, you know that you consider any set, you just need the cardinality. So you are saying you should have a R structure on 5 6. That means you can say you should have an R structure on 2. That is the requirement you need to check, because it says an R structure. So there should be an R structure. Doesn't need to be 1 or 2. There just it should exist. So for example, in the previous question for 5, when you take so for example, when you have 4, there are no children's for 4, and this is going, 5 is always going to appear in this situation. So you should have a structure on 5. So R of 5, so how many children are there? No children. So that means the set is 5. So R of 5 should be something, should be non-empty, should be greater than or equal to 1. So we are saying there should be an R structure on the set of children's. So that means set of children's is just 5. So R of 5 should be greater than or equal to 1. But what does what happened in this situation? You know that there is no uh, no structure on 5. There is no structure on empty set. So so you cannot, because you know that if cardinality of U is 0, it is 0. There is no structure on it. So that thing have gone wrong that there. And in this situation, for every cardinality of u, or for, so if you take this, then you have r2, and you know that r2 is non-empty because u is 2, cardinality of u is 2, then this is going to be just 2. So you will have at least you will have exactly two structure on 1 plus epsilon. Sorry, there are two structures. There are two 1 plus epsilon structures.
Yes, ma'am.
Okay, so but the requirement is you should have have an structure on the set of childrens. So you count the set of you count the cardinality of set of childrens for every element. So for 1, for example, you have 2. For 3 it is 1. For 4 it is 5 and 6. Sorry, for 4 it is 2. So you just count the cardinality of the set of childrens for every element and check if there exists an R structure or not. If there does not exist any R structure, then you can just say this could not be a valid R enriched rotatory.
Okay. First question now. We have one structure. The suitable diagram can you draw, ma'am?
Uh,
These structures are wrong.
yeah, these pictures are now I cannot draw any structure because in this situation there cannot be any structure, because you know that these are rooted trees. So at the end you are going to get zero, like you are going to get something which does not have any children. That means you need to have a structure on r5, which it is not there. So whatever structure you draw, it cannot be a valid one.
Okay.
So for example, if you want to have it, then you have to go with just 5. There is no element, so you consider the structure. So when you try to consider it, so here so you are considering the rooted structure on u, so you just take nothing, then there is no so basically that is also not okay, because rooted trees have to have one element because root should be there. So if you have even one root, if you consider a1, if you consider this as your rooted tree, then again there are no children of 1. So r of 5, now you need to have an r structure, then r of 5 should be something, but it is empty, so you cannot draw this even. So there is no possibility you can have any valid structure on it.
Okay.
So you just need to calculate the cardinality.
Okay,
And
ma'am.
not cardinality, but if there exists one, then it is okay. If there does not, then this is going to be wrong. So for example, if somehow, for example, in this situation, r of 5, for example, uh, or maybe if you want to modify, there is one option. So you have x plus e3, right? You add the structure, so you can add, for example, in this one we have added 1. So if you take this to be your r, 1 plus x plus e3, then 1, make sure that there is one structure on 5, right? Because 1 is what? 1 of u is exactly u if u is equal to 5, and like 5 otherwise. So this means there is one structure, because this is exactly 5, right? There is one structure. So when you take u to be 5, then you are having a structure. That was the requirement you need. Then in that situation, if you consider this r, then what is the requirement you need? Phi has a structure. That was the thing which was missing. So in this situation, you are having r of u. The cardinality, if you check, 1 is there is one structure when it is 0, 1 or 3. Okay, and 0 otherwise. So if the number of childrens are not from the 0, 1, 3, then there will be a problem, but otherwise you are okay in this situation. So if I add this situation, then actually all the structures are going to be okay, because 1 has 3 childrens, then it is okay. 3 has 1 children, that is okay. 4 has 0 children, that is okay. 5 has 0 children, that is okay. Okay, so because you know that 0, 1, 3 is okay. If you have anything else, for example, For example, if I remove this, then there will be a problem. Then it cannot be a valid structure, because 3 has two children. Okay, 3 has two children, 1 and 2, but there is no structure on 2. So you cannot draw this. Like, there is no R structure on the set of children's. Set of children's has cardinality 2. So R of 2 is 2 is 0 in this situation, because there is no 2. For 2 it is just 0, there is no structure. So if you consider this is going to be wrong. Is that clear?
Yes, ma'am.
Okay. Yeah, these are all the questions which I wanted to discuss.